Well, good morning, everybody, and welcome to Ellensburg, Washington, USA. On the screen right now is our title slide for today's talk. Very excited for this talk. Trevor Waldien from South Dakota School of Mines has made his way out here to Ellensburg, Washington, and in just a few minutes you will be hearing a presentation entitled, "Why is Alaska Curved? Tectonic Development of the Alaskan Orocline." I'm 5x5. Thank you for the folks in the live chat for that report. Let me get on camera and I can say hi to a number of you. Hey everybody, how's it going today? Thank you for coming. Thank you for tuning in live. We have many live viewers, approaching 100 live viewers, and more will be trickling in for this very important talk. Important for a number of reasons, including Alaska A to Z will be starting November 5th or November 6th, the first Thursday in November of 2025. And I have most of my thoughts together on how we will start, but I think today's talk will give me some new ideas as well. Where are you viewing from today, assuming that we're still functional, and then when I feel like we're ready to go and settling in, I will turn on Trevor's microphone to make sure that we can hear him as well. Webb Lake, Wisconsin, that's North Scotty Nerd. Spokane, Washington. Cincinnati, Ohio. Salem, Oregon. Boise, Idaho, that's Jennifer. Salem, Oregon, I just said that. You're awesome, Arkansas. Oregon Central Coast. Vienna, Austria, hello Richard, what's up? Beautiful Menominee, Michigan. Tukwila, Washington. Kingsgate, Washington. Olympia, Washington. Rockland, California. Yeah, we're getting the band back together. We're getting back in the flow of doing these live programs. It feels great to be back with you. Coast Cobb, Connecticut. Eugene, Oregon, that's Steve. Fabian, Alberta, that's Roy. Winter Garden, California. Geology Grandma says hi from Orlando, Florida. San Antonio, Texas. San Jose, California. Glasgow, Scotland. Good evening, Paul. Helena, Montana, or Helena, Montana for those that actually live in the state. Selwood, Oregon. Raleigh, North Carolina. Charleston, South Carolina. Prosser on the Rocks. Fremont, California. Arnhem, the Netherlands. Hello, Tom. Well, the hits keep on coming. Gainesville, Florida. Argyll, Scotland. Enola, Pennsylvania. Hamlin, Germany. Milwaukee, Oregon. Hi from Seattle, says Stevie Pinhead. Lakeview, Oregon. Daniel loves the education. I love you for being here, Daniel. Robert Hildebrand Jr., Lakeview, Oregon. Not Robert S. Hildebrand from Tucson, Arizona? Very good. And so on. Thank you. Let me run through the stations real quick. I'll go find our speaker, get a microphone on him, and we'll get going. But if you've been watching this patiently in replay, you're like, is this thing ever going to start? Yeah, it's going to start in 10 minutes. Okay? So you can skip ahead to the bookmark if you haven't done that already. The bookmark will say, lecture begins, or something like that. Thanks for joining us today. All right. We got face cam, and Jordan Carey is going to be doing the introductions today. Slides and face, slides, 2 cams, triple threat. That'll work. I'll give you the title slide again while I adjust the wide cam and give you a shot of the room with the intention of giving you a sense that you might even be here. Trevor, our speaker, has just magically appeared. He did not need to be chased down the hall. Maybe he was chased back into this room. Yeah. And Trevor's...
found me in Yakima.
And wait, what's going on? Why is that doing that? This is what I want to use. All right, get your coughs out now, son, before I mic you up.
That's right.
It's okay, though. You're under the weather. You're fighting through it. So viewers, you're just going to have to deal with some coughing from our speaker. Can you do that? He's not going to infect you through the YouTube. I don't think YouTube is sophisticated enough yet to do that.
Computer viruses are not the same.
Oh, see? Computer viruses. That's slick. That's very slick.
Situational humor.
Ah, he can turn it on when he needs to, folks.
That's right. Otherwise, I'm boring.
All right, we got 200 people watching live.
Holy smokes.
And thank you for being willing to use the little gold plated thing.
Yeah, no worries.
So we're just going to put this right here. We're going to flop around. I think we're good. So
okay, I can take my jacket off too if you think I should.
Either way is fine. The jacket looks good.
Oh,
if you're not going to be too hot.
No, I'm good temperature. That's why
good.
I like it. So.
Let's just keep chatting, Trevor. Viewers, let me know if you can hear Trevor, please.
Can you
So you
hear
landed
Trevor?
at SeaTac what time, and by the when did you get to Ellensburg last night?
I landed at SeaTac at about 3:15.
Nice.
And then I took a shuttle bus to Ellensburg, got into town around 7 p.m.
Took the shuttle.
Took the shuttle. Yeah, I was actually, I was meant to take the 7 o'clock shuttle, but because I assumed my plane would be late, so I booked the latest shuttle I could.
Right.
But I got in early in time for the 4 o'clock shuttle, and they let me on. So I got here at 7. I was supposed to leave SeaTac at 7 and get here around 9:30 or 10.
People are nice out here.
People are
Trevor.
nice, yeah. So.
I've done that sprint too. It's like
Yeah.
I can get this 4 o'clock thing if I get over there quick.
Well, I mean, last time I flew out of Rapid City, I was delayed for hours and hours and hours, and so I just planned on being delayed.
Yeah.
I don't think well, yesterday was probably the first time I've flown United and not been delayed. But unfortunately can't fly Alaskan Airlines out of Rapid City, so I have to do other things.
Well, I got bad news. This broadcast is being sponsored by United Airlines.
Well,
So,
United Airlines, get it together. You have a disenchanted customer.
Oh, Alaska. Good, good. Okay, your mics is
it's working?
It's working for them, so
Okay.
just be aware that when you start talking shit with Jordan, they're all going to be able to hear you.
That's right.
Okay. All right, we are good. Everything's rolling.
So I'm gonna.
See, Nat got me set up last time to switch cameras and have it not switch up there, but I've undone whatever Nat did. So we're back to the old ways of
On purpose or on accident?
on accident. So he was like, "Are you sure you want what's up there? Are you sure you want the broadcast to go on the screens?" I'm like, "That's what I've done for 3 years straight." He's like, "No, you've never done that." I'm like, "Yes, I have. I've always had."
But like us as people.
Yeah.
Like or the person down in the corner, right?
All these cameras, Nat's like, "You don't ever really have these up on the screen." And I'm like, "Yes,
you definitely
for
did.
3 straight
yeah.
years."
You have to slide up and then the person down in the corner.
Nat, can you hear this? Nat, are you watching right now? Jordan is backing me up. So anyway, he got me off of that, and now I undid what he did. Whatever. So we're back to, we're going to get a nice profile shot. We're going to get the man bun in profile.
The
Jordan.
man bun.
Right here. That's, well, no, it's not. Okay, now I'm just freelancing. I want to give, what's going out right now? I'm too comfortable. See? Chris Mattinson, Hannah Shamloons, speaking with each other. That's rare. Just kidding. All right. Guess we'll put
Do you
this.
have the side camera?
Yeah, that was it. I'm gonna swing the wide camera around. Jordan wants to know which camera
Well,
is.
I'm just making sure that
That you're on camera.
No, that you're not going to have a moment right when it starts up. So I thought that's what you were trying to figure out right now.
I will. Oh, let's do it. So right now they are seeing. That's the broadcast. They are seeing that. So we're going to swing around.
You just pan with the mouse. Weird.
Don't question me, Jordan. I usually use the clock as my little anchor, but now we got this frickin' ADA table, which I'm sure is not being used this quarter, but whatever. So we're going to be like, little Jordan's going to be right in there. And Trevor, when we introduce you, you can stand right up at your station if you like, because you'll just be rolling right away. And
You're going to tell me where to stand?
you can stand right next to me. one thing that sometimes freaks people out, although you're a cool guy, I don't think it'll freak you out. Occasionally you'll look up there and you're like, that's me up there. Get my slide up there, man. So like,
here?
yeah, so I've got whatever's going out to the
Okay.
home crowd is going up, and I've got these different cameras.
Okay.
So occasionally they'll be like, and I'll like, hang on, I'll get back to your slide.
Okay.
Or
Will
you
that
might-
one always be the slides?
No,
That one will switch around too?
they're switching.
Okay.
And occasionally you'll be in the lower left covering up some text, and you're like, hey, and then I'll go, sorry, and then
Sorry.
I'll get you away.
He's pretty good at recognizing when you want to be down there and when you don't want yourself big screen on the phone,
Gotcha. Okay.
from what I've seen in the audience.
It's just a slight little weirdness, like you look up and say, and then, there we go, this guy finally switched, because I'll just be sitting here
Yeah.
playing around. You're cool though, Trevor, you're
Yeah.
cool.
Oh,
I can't
man.
fluster you. Okay,
Sometimes.
all right. Oh, we got, Miss Koff, hello. Silicon Valley, eating a little working lunch for you. Very nice. Yeah, you guys are still seeing the title slide, right? Pretty sure you are.
I already got 81 thumbs up and haven't even said anything yet.
That's your reputation.
It's because there's a picture of a dog. That's
that-
Cobalt, the geologizing dog.
Is it really?
Yeah.
So I emailed Sean, I said, see this thing with Trevor, I want to do the same thing with you. And he's like, I can do it, but I'm not as charismatic as Trevor. Like, okay.
Sean's
well,
always saying nice things about me, but the thing that you gotta be aware with Sean is that he's full of it.
Oh,
I'm just kidding.
well, good. I'll get that ready.
Sean is very smart and sells himself short.
I know a lot of people like that. Okay. Oh, there's a good vibe in the room. There's a good vibe in the room. A very serious academic vibe in the room.
Typical
That's my
classroom where
interpretation
the
of
front rows
that.
are empty and the back rows are full.
This is where I teach 101.
You hear this okay, Hannah? Okay, not too much feedback? Good afternoon, everybody, and thank you for coming today. I hope that you enjoy today's talk. In fact, I'm so confident you will enjoy today's talk. Late arrivals, come on in. We're just getting started. Plenty of empty seats down here close to the front. Thank you for coming. This is the second Friday in a row that we've had a noon talk. Next Friday is October 17th. Ain't nothing going to be happening here, okay? We're taking a Friday off next Friday, the 17th. But we finished the month of October with back-to-back Washington Geological Survey talks, Friday, October 24th, and Friday, October 31st. So Mitch Allen talking about landslides, Emily Richard talking about post-fire debris flows. Excited to have them both here. If you were not with us last week, a gentle reminder that you need to do some paperwork if you haven't, involving permission to get you on camera, or even documentation you want to stay off camera. And Bree McGinnis, standing in the back, is the person to see that. You only have to do it once for the entire year, but if you haven't and you're a student here, please do so. A reminder that this half of the room basically is, you're on camera occasionally, although you're not right now, but you guys back here are totally off camera. President Wolpart, nice to see you today. Thank you for coming. Okay, so that's the deal there. 504, 304. If you're in those classes, Bree's your instructor. Check in with her as well. Enough of this announcement stuff, which is minor. We need some major action. And to do the introduction for our speaker today, Jordan Carey, who works in the geology department here. Jordan, can you introduce our guest, please.
Thank you, Nick. Don't clap for me. All right, thank you all for coming. It is my personal pleasure to introduce our guest today, Dr. Trevor Waldien. Dr. Trevor Waldien. He comes to us from South Dakota School of Mines, where he's currently been a faculty member there for the last 5 years. Trevor and I's paths crossed about 10 years ago. Trevor was doing his master's at the time at UC Davis, where I was thinking about going to grad school at the time. I was there on a visit. I met Trevor at a bar that night, I think, and he said something along the lines of, "Hey, I'm Trevor. I like to mountain bike." And I was like, "Oh, I guess I know where I'm going to grad school now." Decision made.
The flattest place in the West.
Yeah, that's right. Flattest place in the West. Since then, Trevor's made his way out to South Dakota, done some other things along the way that he's going to tell you about here in a moment. So without further ado, please welcome Trevor Waldien, who will be answering the question today of why is Alaska curved?
Thanks, everybody. I'm happy to be here. I've known about this department for a long time, which I'll show you in a second. So I'm glad to be here talking to you about some work that I've been doing in southern Alaska. Before I get into that, I've been asked to give a brief comment on my journey through the geosciences, and so I'm doing that with this slide here. And you can track my journey along a geologic map of Western North America. So I'm a Pacific Northwesterner at heart. I grew up in a small town in southwestern Oregon named Coquille, Oregon. My whole family works in the timber industry. And my first exposure to the geosciences was probably seeing signs that look like this right here, if I can get it to work in the middle. Tsunami hazard zone signs. I remember crossing these signs going to the grocery store with my mom as a kid. And didn't ever think really what they meant, just that sometimes big waves could come and we need to go to the mountains when that happens. And then fast forward a handful of years, I'm in high school. I'm mostly concerned with dirt bikes and football, but there was a teacher at my high school that taught a geology class who actually made the trip up here. So I'm going to pick on Frank Ladke, who's sitting right in the middle back there. So Frank had, my understanding anyway, is that Frank had worked for the Oregon State Geologic Survey for many years, decided to be a high school teacher for reasons I don't know, and got a job in Coquille, Oregon, and taught a geology class, and I just happened to take that class, and we went on field trips. We went to the mountains and saw seashells. We went to the beach and saw basalts and things like that, and I said, holy smokes, this is pretty cool. And I was about 16 years old, trying to figure out what to do with my life, and I decided that I was going to go to college and study geology. I went to Oregon State, which is the Orange Star there in Corvallis, Oregon, and I learned very quickly that I had very bad study habits. And I seriously thought about dropping out because I didn't know much about college, but I figured it out. Figured it out, ended up applying, at my time at Oregon State was fun. I got to do field camp with Central Washington University. I exhumed these photos. These are from 2011, field camp in Mitchell, Oregon. And developed a joy for mapping and deformed rocks, and then decided to apply to grad school, where I learned that I wasn't a very strong applicant for graduate school, and I mostly heard crickets from my grad applications. I applied to 2 schools. One was UC Davis, and the other was Central Washington University. And I heard back from UC Davis first, and as they say, a bird in the hand's worth 2 in the bush, so I went to UC Davis. Went there for a master's, ended up staying for a PhD, got working in Alaska on some projects in the Alaska Range, which on my map here is there. And was set up to finish my PhD in spring of 2020. I'm not sure if you guys remember what you were doing in spring of 2020, but I was sitting on my couch writing my dissertation and realizing that the world was dying. Fortunately, I was able to stay in school for another year. I applied for basically everything under the sun. I applied for a job in South Dakota, and as was the deal with graduate school, I I was offered a job. I had many other irons in the fire, but a bird in the hand's worth two in the bush, and so I moved to South Dakota during the middle of the pandemic. Which moving from California to South Dakota during the pandemic basically meant the pandemic went away, at least in terms of public perception of the pandemic. But anyway, so I've been in South Dakota ever since. I teach classes in structural geology, mapping, geochronology, things like that. So that's just a little bit of a roadmap of where I've been. But enough about me. You all are here to learn about Alaskan geology today. And so my talk is titled, Why is Alaska Curved? The Tectonic Development of the Alaskan Orocline. And I just want to highlight my main collaborator on this project is Sean Regan at the University of Alaska Fairbanks. And we've had a project going for the last handful of years in a small mountain range down here in southwestern Alaska called the Wood River Mountains, which is right there. And being on the other side of the curved part of Alaska, we've been thinking a lot about why Alaska is curved. And so the talk today is basically our ideas on why Alaska is curved. So I'll be talking about these things called oroclines today, and oroclines are not the most mainstream thing taught in undergraduate or even graduate geology programs, so I want to define my term here before I get going. So what is an orocline? Like many geology terms, you can break this word down into its roots and its prefix. Okay, so oro comes from the Greek word oros, which means mountain, and other geology words that we have with this same root are origin or orogeny. Those are mountain building events, right? Cline, also Greek for kleinen, translates to slope or a fold, and other geology words we have are things like anticline, syncline, monoclines, or basic geologic structures that are folds. So an orocline is a mountain belt that is curved or folded. Okay, so we're going to be talking about curved mountain belts today. Why is Alaska curved? Alaska is a curved mountain belt. These things are everywhere. They're on every continent. They form currently in active tectonic settings. They formed way in the past in ancient geologic settings. Here's a couple examples from Europe. We've got the Western Alps over here, where you see Italy going into Switzerland. We've got curvature in the Western Alps, and I think, there it is. So curvature in the Western Alps, and if you go over here to Eastern Europe, you can see this curved mountain range through Eastern Europe here called the Carpathians, which is sort of a famously studied orocline because it makes this weird, almost 180-degree bend. So Europe has some oroclines. South America has some oroclines here in the Andes. We've got the Bolivian orocline right in the middle, something you're probably very familiar with. And then in southern South America, we've also got the Patagonian orocline, which you can see as the Andes here are generally going north-south. And so South America is turned on its side, obviously, I hope. So the Andes go north-south, and then they turn off to run east-west. So that curvature in the southern Andes is called the Patagonian orocline. And today we're talking about North America, and there are many oroclines throughout western North America. Here's just a couple of them that are relevant for our talk today. One is the Mackenzie Mountains in northwestern Yukon. You can see there's curvature in the mountains that go out here in eastern Alaska, curve through northwestern Yukon right there. And then today we're talking about the Alaskan orocline, which I probably don't need to point at. It's just this curvature of big peaks that you see through southern Alaska. So how many of you have noticed that about Alaska before? The mountains all curve right through the middle of Alaska. So that's what we're talking about today. Why does that curvature exist? Oroclines have been studied in a fair amount of detail, mainly by the paleomagnetic and structural geology community that focuses on fold and thrust belts. And the folks that have worked on this have come up with basically two models for orocline formation. The first model is what they call a primary mode for developing oroclines. That's what's shown in the top here with the red arrows in the block diagrams. And in the primary mode for orocline formation, the orocline, or that curvature, is going to form as the mountain belt is building up and thickening the crust and making the big mountains. So the way to do this, or the ways to do this, is with velocity gradients along strike of the mountain belt. You can also do this by changing the thickness of the crust in the mountain belt along strike, and that will cause curvature in the mountain belt. You can also do this with some pre-existing geometric complication in the crust before the mountain building starts. Okay? So there are ways to develop curvature in a mountain range as the mountain range is forming. That's what we call the primary mode. The secondary mode is to build up a mountain range like we're showing here in the top center. So you build up that mountain range by shortening in one direction, and then what we're going to do is switch the tectonic forces and then shorten the mountain range on end. So an analogy would be with our stick here. We've built up the mountain range that is our stick, and then we're going to push on it from the end, and it's going to curve that mountain range. So we're going to buckle the mountain range after it formed. So in primary oroclines, the curvature is going to develop as the orocline, or as the mountain range develops. In secondary oroclines, the curvature is going to develop by a subsequent deformation mode acting on that mountain belt. The fold and thrust belt community, or the community of structural geologists that work on fold and thrust belts, have also come up with a couple of explanations for why primary oroclines might form in mountain belts. One way to do it on the left here is to change the wedge thickness. So if you think about a bulldozer pushing dirt, the triangle of dirt in front of the bulldozer is going to have some wedge angle, and a bigger pile of dirt is going to have a larger footprint, and a smaller pile of dirt is going to have a smaller footprint. So if you change, an analogy, you change the thickness of the dirt, or basically you change the thickness of crust in your fold and thrust belt along strike of the fold and thrust belt, you can develop curvature in the fold and thrust belt like we're showing down here in the lower left that's simply related to the thickness of crust that is in that fold and thrust belt. So you can curve the mountain belt that way. Another way to do it is to change the strength of the mountain belt along strike. So one thing we've learned about these piles of dirt that bulldozers push is that the strength of the material in that pile of dirt, or in this case a fold and thrust belt, controls the taper angle. And piles of dirt or mountain belts that are weak will have long, skinny taper angles, so a lower angle that covers a larger area. And strong materials will have a shorter taper, or a steeper taper angle, so a smaller footprint that is more steep. But if you have a single mountain belt that has different strength along strike of that mountain belt, like we show it here in the upper right, you can generate curvature in the mountain belt simply related to a long strike variation in the strength of the crust that is involved in that mountain building process. Okay? So two ways to make a curved mountain belt that are just simply related to the mechanics of how the crust deforms. Okay? And people have thought about this quite a bit in the context of fold and thrust belts. The problem is, when it comes to Alaska, is that Alaska is not a fold and thrust belt. Alaska is an orocline that is defined by curved strike slip faults. We can see that in this image here from this Twiss and Morse textbook. Here in the Canadian Cordillera, here in southwestern Yukon, southeastern Alaska, the faults are generally straight. They strike to the northwest. And then you get through central Alaska, and all these faults curve down and become southwest, northeast striking. And what this image here is showing in these dashed lines is that the curvature, or these dashed lines show the projected trace of the fault if all the faults were straight, but you see that they don't follow that projected trace, they are curved. So this orocline in Alaska is an orocline defined by curved strike slip faults. So all that stuff I was telling you about, the strength of the crust and the bulldozer pushing the dirt, doesn't apply here because this is not a fold and thrust belt. Okay, so we need another explanation for why this orocline exists, okay? And if that's not enough of a sales pitch to you, I'll just tell you this is the structural geology textbook that I was raised on. This is the one we used at Oregon State, and then it was written by people at UC Davis. So at UC Davis, we use this textbook as well. And most structural geology textbooks don't really talk about oroclines, actually. This one does, and the one they use as an example is the Alaskan orocline, which I probably made the case to you by now is kind of a weird orocline. So this is a textbook example of this process, but it's actually a weird one, and we don't understand it very well. So the point I'm trying to make right now is that we need a better explanation for why this structure exists. So what I want to do for the next handful of minutes is walk you through the evolution of thought on the Alaskan orocline, and we're going to go all the way back to the 1950s. So this is, as far as I can tell, this is the first paper that was ever written about the Alaskan orocline, and I believe this is where they define the term, is Carey, not Jordan Carey, 1955. all right? And in this image here on the left from Carey, they notice that Alaska is curved. So Alaska is down there in the lower part of the image, right there. The ocean basins are black, so the Pacific Ocean is there, the Arctic Ocean or the Canada Basin is there, and then you see Alaska is curved. And the hypothesis presented by Carey to explain the Alaskan orocline is that buckling of Alaska to make this big fold is related to opening of the Canada Basin. And you fast forward a few decades to this image from Coe and others in the late 1980s, they're showing basically the same thing, is that if you've got some sort of rectangle and you bend that rectangle, you'll make curvature on the bottom side of the rectangle, and you'll open up a big basin on the top side of that rectangle. And they use the term sphenocasm. So if you're looking for a Scrabble word, that's a good one. Okay, sphenocasm. So in Carey's model, the Canada Basin is a sphenocasm that is related to buckling of Alaska and development of the Alaskan orocline. So that's one of the early ideas about development of the Alaskan orocline. Move forward now to the 1980s. There's a person named Rob Coe who was a paleomagnetist at the University of California, Santa Cruz. And they worked a lot in Western Alaska doing paleomagnetic measurements. And he came up with some newer ideas on the Alaskan orocline, or he and his students did anyway. And the idea that they settled on is related to this image here. This is from an introductory textbook. But basically their argument is that the buckling or rotation of Western Alaska is genetically tied to opening of the North Atlantic and breakup of Pangaea. So basically seafloor spreading here, extension in the North Atlantic. North America is going to be moving to the west. Eurasia is going to be moving to the east. You go around the world to the other side. Here now you're in Siberia. Oh, I lost my arrow. Here we're in Siberia. Now Siberia is moving to the east. North America is moving to the west. Alaska's caught in the middle, and it's just going to buckle to get out of the way. All right, so that's the idea that was presented by Coe and others in a couple papers in 1985 and 1989. Coe also had an explanation for the strike-slip faults that we see throughout the Canadian Cordillera into Alaska, and his model is basically this here, is that you've got a series of strike-slip faults. This is that same rectangle that we saw a minute ago with the sphenocasm. But here you've got a series of strike-slip faults, which are these dark lines that are chopping up the crust. And when you get into the orocline axis, you're going to have a series of small blocks that will rotate, and it'll open up these little basins right along the orocline axis. Okay, so Siberia is going to be pushing on the Cordillera. North America is over here on the right side. And we're going to kink Alaska and open up these little basins along the axis of the Alaskan orocline. And the strike-slip faults help accommodate differential motion as the whole thing is bending. Okay? So if we think back to our orocline models that I was talking about a minute ago, this is basically the secondary orocline model. We've built up a mountain belt in the Canadian Cordillera, and then we've got convergence between Siberia and North America that's going to end load that orogenic belt and buckle Western Alaska, making the Alaskan orocline. Okay, any questions about that before we move on? So that's the history of thought. Yeah?
And why does the Aleutians curve back the other direction?
We'll get to the Aleutians. Can you hang on 30 minutes or maybe 25 minutes? I promise we'll get there. Okay. So I like to think about things in terms of maps. Maps make sense to me. So here's a map, a Google Earth image of basically all the stuff that I just said. So we've got North America moving to the west, Siberia moving to the east. We've got strike-slip faults, right lateral strike-slip faults in the Canadian Cordillera that are shipping crustal blocks out toward the Bering Sea. And then Alaska gets caught in the middle and is going to rotate counterclockwise, buckle Alaska, creating the Alaskan orocline. And again, this is our secondary orocline model. However, I wouldn't be talking about this stuff today if there weren't a couple issues with it. One issue is the timing. So what we know about the paleomagnetic rotations of Western Alaska is that the majority of this rotation took place between about 65 and 45 million years ago. Okay, so a pulse of rotation about 20 million years long, 65 to 45. However, opening of the North Atlantic initiated in the late Cretaceous, but has been happening ever since. And our strike-slip faults in the Cordillera have started about 85 million years ago. and are still active today. So our drivers for this rotation, this buckling of Alaska, have been ongoing since the late Cretaceous, but the actual process of buckling Alaska was a relatively discrete event. So it doesn't make sense to me how we can have a discrete rotation event that's driven by these continuous processes if those are the only things related to this rotation. So I think that's a problem. Problem number 2 is the strike-slip faults. So since this image was published, we've learned quite a bit about the timing and magnitude of displacement along strike-slip faults in the Cordillera. And the main message for right here, right now, is that the rocks that would have had to be in Alaska in order for this strike-slip model to work were not in Alaska. They were in Canada, or many of them were probably in Washington or California at the time. To make that case, this is just a summary map of the big strike-slip faults in the Cordillera, and I've got on here color-coded stars for displacements on each of these that give you the timing and magnitudes of displacement. So on the Tintina fault here, the red stars give us about 430 kilometers of displacement in the late Cretaceous to the Eocene. The Denali fault, where I did my PhD, we've got 480 kilometers of displacement from 52 to 0. So it's still an active fault right now, had a big earthquake in 2002. And then the Border Ranges fault, these green stars here, give about 1,400 kilometers of displacement that took place from about 85, it's not clear when it shut off, between about 50 and 35 million years ago. So if you just add up those displacements, and there's likely additional displacement that's older than all of those time periods, now what we're going to do is take this crust and move it back farther south, and you can see if you just add those up, it's not hard to find 2,000 plus kilometers of strike-slip displacement in the Cordillera. The other problem with this existing orocline model is that the oroclinal bending of Alaska overlapped in time with the shortening that created the Cordilleran mountain belt. So we talked earlier about this two-phase orocline development. We build up a mountain belt, then we bend it. That can't work if our mountain belt is still forming as the rotation is happening. So to make that case here, and we'll talk more about this in a second, there's metamorphism all along the length of the Cordillera, from right here in the North Cascades all the way to central Alaska, that records significant amounts of shortening in the Cordillera from 72 to 57 million years ago. So the Canadian Cordillera was still building up as a mountain range in the late Cretaceous and the Eocene while Western Alaska was rotating. So this model of building up the Canadian Cordillera and then buckling Alaska because of the North Atlantic opening doesn't quite work with the timing of mountain building in the Canadian Cordillera, and it doesn't quite work with the strike-slip displacements that we now have a better grasp of in the Canadian Cordillera. So, why am I here? Well, I'm here to present to you what I think is a reconciliation of these problems. We've got 3 problems. The timing doesn't quite work, the strike-slip fault displacements don't quite work, and the mountain building doesn't quite work for these existing models of why the Alaskan orocline formed. What I want to do right now is spend some time talking about the mountain building process, because I think that's pretty important moving forward for my tectonic model. So we'll talk about that a little bit, and then we'll come back to the paleomagnetic data and talk about rotation of Western Alaska, and then we'll wrap it up with some tectonic synthesis. This is a very busy figure, and I'm not going to talk about it in detail, but I've left it busy on purpose to make the point to you that Western North America, and actually probably most active plate boundaries anywhere on Earth, are made up of fragments of lithosphere that did not form here. Okay? So every different color on this map is a different map unit, different body of rock. Some of them have genetic ties to North America. Those are here in blue. Anything that is not blue has a genetic tie that is demonstrably not North America. All right, so our crust here in Western North America is not part of North America when it formed and came to North America, accreted to North America by tectonic processes, and became part of North America. Okay, we call these things terrains. And it's spelled kind of weird, T-E-R-R-A-N-E, terrain. All right, so this is a busy map, not going to explain all of it. This is a much simpler version of that map that's relevant for us today, and I will explain this stuff. Okay, so what I've done here is I've reduced that map to, I guess actually technically 4 terrains. that are relevant for this Orocline story. So anything that's not colored here, I'm just not going to worry about, and it's not relevant for this story. The purple are what we'll call previously accreted Cordilleran terrains. Okay, and by previous, I mean something before late Cretaceous. Okay, some of these fragments are Laurentian affinity, some of them are not. For our purposes here, it doesn't really matter. This is basically the backstop of this orogenic belt. This is the stuff that gets hit when the other things collide. Okay? The blue, or the light blue here, is what we call the insular terrains. The insular terrains is an amalgamated island arc complex. Think modern day analog like Japan or Sumatra, something like that. There's a little bit of continental crust in there, but by and large, these are oceanic island arc rocks. Basalts, andesites, most of them are very green and low-grade metamorphosed, pretty ugly rocks. Okay? But this represents an island arc that collided with North America, and that collision built up the Cordilleran origin. Okay, so the insular terrains are not part of North America, or they did not form as part of North America, they collided with North America. The yellow here are what we call the Chugach terrains, and they are the accretionary prism to the insular terrains. Okay, so for every island arc that you can think of, there's a subduction zone, and that subduction zone has an accretionary prism associated with it. These yellow rocks are those off-scraped oceanic fragments that are that accretionary prism. There's blue schists in there, there's eclogites in there, there's ophiolites, there's a whole lot of sandstone, subduction accretion rocks. And then lastly, we'll talk about it a little bit here at the end of the talk. I've left on here the Yakutat terrain. So who's familiar with Silesia? Excellent. All right, so Silesia is down here in the Pacific Northwest in the Columbia Embayment. Yakutat's interpreted to be the other half of the Silesia Oceanic Plateau that went on a northern adventure, slid up the coast along the Queen Charlotte Fault, and is now converging with southern Alaska. So it formed right next to North America, but it's not Laurentian crust, and it formed at about this latitude and has found its way up to Alaska. So that's our fourth terrain. So we've reduced this map to a couple things that are more digestible, and we'll track, and we'll actually use this map a lot as I move forward in the presentation today. So what do we know about this insular terrain thing? I've told you it's this arc complex that collided with North America. How do we know about that collision? What do those rocks look like? When did it happen? We're going to talk about those questions right now. To answer those questions, we're going to look at the Gravina Basin in southeast Alaska, and we're also going to look at the Kahiltna Basin in south central and southwestern Alaska. And I'm going to show you a couple cross sections that are very generalized. And you can imagine these cross sections I'm showing you could be any of those red bars there. They could be in central Alaska, they could be in southeast Alaska. It's all basically the same story at any of those three places along the margin. Okay, so here's the cross sections. We've got two timestamps here. In the top, we've got a timestamp from 90 to about 105 million years old. And this is a time period that represents the youngest sedimentary rocks in those basins. So the interpretation here is that as the insular terrains are converging with North America, there's a sedimentary basin in between them and North America. As it gets closer and closer and closer, that sedimentary basin is going to close. It'll dry up. No more sedimentary rocks are going to be deposited in that basin. So at that time, about 90 to 105, we've got the insular terrains on the left, which is the west side. We've got a subduction zone dipping off to the east beneath North America, and then we've got two types of sedimentary rocks in that basin. We've got the darker green is the back arc basin to the insular terrains, and then the lighter green is a forearc, sort of forearc basin accretionary complex type environment that is built on the North American side. This basin is going to continue to close by subduction, and here at 82 to 57 million years, we see imbrication of those two sedimentary basin packages. North America is thrust on top of all of those sedimentary basins. Those sedimentary rocks are placed under the North American crust. They're metamorphosed, they're sheared up, and we're going to look at some of those rocks here in a minute. Okay, so right now we're going to look at a thin section that was taken from a place that we think formed about inside of that red circle. So here's what the rock looks like. This is a thin section map that we collected on the electron microprobe. This is a map of magnesium. So most of the things we're seeing in here, the purple are garnets, The yellow are biotite. Okay, so this is a garnet, biotite, muscovite schist. There's actually sillimanite and kyanite in these rocks as well, but those aren't going to show up in the magnesium map because there's no magnesium in them. Another thing you'll notice in this rock here, aside from the minerals and the colors, is there's this really strong shear fabric in this rock. Do you guys see the lines dipping off in one direction? So this is what we call a C prime fabric. Is anybody familiar with SC myelinites? Does that mean anything to anyone? All right, so if you take an SC myelinite and you keep straining it, you'll develop what's called a C prime fabric, which is what we see here sloping off to the left. And this forms at really high shear strain. That's the important thing here. This rock was deformed at really, really high shear strains in a shear zone, okay? In this rock, we can map out all the different elements and the minerals. We can also find these little minerals called monazite. Anyone familiar with monazite? Yes. All right, so monazite is a rare earth phosphate, and as part of the rare earth elements that it incorporates quite a bit of uranium and thorium. Because of that, we can date the monazite using uranium, thorium, lead dating, okay? So we've done that for this exact rock and many others just like it, and we see some cool patterns here in the monazite maps and the monazite dates. So over here, this is a map of yttrium, which is a common element that monazite takes in. And what we see generally are low yttrium cores and high yttrium rims on these monazites. So the bright color here, the kind of yellowy white, is very high counts of yttrium, okay? And when we put laser spots on these monazites, which are the circles here, we get dates in the range of about 62 to about 70 million years. And there's a systematic relationship where the lower yttrium cores give older ages, and the younger yttrium rims give younger ages. So that's internally consistent because we expect the younger rims on the outside to give younger ages. My colleague Sean Regan, who's a metamorphic petrologist, has done pressure temperature work on these rocks and other rocks like that. And so we're showing that here on the left. This is a graph of pressure and temperature, and you can see in 3 different places, South Central Alaska, Southeastern Alaska, and Southwestern Utah. We've got similar PT curves for these rocks. We're looking at things in about 0.8 or up to about 0.8 gigapascals and about 650 to 700 degrees Celsius. And then over here on the right, we're looking at the uranium lead data on the monazite from these 3 locations. And this is kind of a busy plot here, but basically it's monazite date versus structural height above garnet in. And the reason garnet is important is because garnet and monazite are related to each other by metamorphic reactions, okay? So if your rock has garnet in it, it likely also has monazite in it. The takeaway from this graph here, though, is that the dates are pretty much all the same between about 72 and about 56, 57 million for these 3 locations. And in all 3 locations, we see low yttrium rims that are older than low yttrium cores that are older than high yttrium rims, okay? So this is telling about the metamorphic evolution of these rocks. The yttrium thing isn't that important. The thing I want to drive home right now is that we're seeing the same thing in 3 different places, all along the margin, okay? Now if we jump down to this neck of the woods, we can see a similar thing also in the North Cascades of Washington in the Skagit Gneiss Complex. Okay, so I'm summarizing other people's work here. I've never actually been to the North Cascades. But if we look at the Skagit Gneiss Complex and we read the papers of the people that have worked on this stuff, we see that these rocks were sedimentary rocks in the mid-Cretaceous between about 130 and about 80. They were sedimentary rocks. After that time, they were metamorphosed to pressures of about 0.9 gigapascals and temperatures of about 700 degrees Celsius. And if we date those metamorphic rocks with monazite, we get ages of about 69 million, and the metamorphic zircons give ages ranging from about 71 to about 61 million. So my point here is that these ages, these temperature and pressure conditions, and these protolith ages are all very, very similar to what we see much farther north in Alaska. Okay? So what this is telling us is that there's a metamorphic event from Washington State all the way to Alaska that took place between about 70 and 57 million years ago. Okay, so here I'm showing these metamorphic localities on a map. The Skagit Gneiss that I was just talking about is down here in Washington State, and then these blue stars as you go up the margin are these other places that we've done work on these metamorphic rocks, dating these metamorphic processes, and unraveling this story of major late Cretaceous to Paleogene shortening and metamorphism all along the margin of the insular terrains. The other thing that's happening at this time is that there's an active magmatic arc that is intruding these rocks. And along the length of the Canadian Cordillera, the igneous rocks of this age are lower crustal plutons that are intensely flattened. These things are shaped like pancakes, okay? There's a great paper from the 90s that wrote about these rocks and calls them the Great Tonalite Sill. Great because it's over 1,000 kilometers long from southeast Alaska down through British Columbia. So that's this really thin belt of burgundy that runs along the margin here. That's the Great Tonalite Sill. So great, it's big. Tonalite, it's almost exclusively tonalite. And sill, it's a tabular shaped body that has been intensely flattened, okay? And this thing's been dated at about 70 million years. So the 70 million year old batholith along the length of the Canadian Cordillera is lower crustal plutons that have been intensely flattened. You go out to Western Alaska, we don't have no Great Tonalite Sill in Western Alaska. What we have are volcanic rocks. We have the upper crust, okay? We have volcanic rocks sitting on top of unmetamorphosed early Cretaceous sedimentary rocks, okay? We'll add in the Paleogene igneous rocks all along the length of the Cordillera. Here, these rocks are not intensely flattened for the most part. Oops. But you see voluminous magmatism all along the length of the Cordillera. These are exhumed plutonic rocks in most cases. You go out to Western Alaska, there's not nearly as much. It's much more widespread. It's not really a belt. It's more like a shotgun blast. And again, primarily volcanic rocks in Western Alaska. Now let's look at sedimentary rocks of this age, late Cretaceous to Paleocene sedimentary rocks. Those are shown in green on this map. Where are the sedimentary rocks? Are they in Canada? No, they are not in Canada. All right, so during this time, we have intense metamorphism and deformation of a batholith all along the Canadian margin. You go out to Western Alaska, we have volcanic rocks filling extensional basins and sedimentary rocks filling those basins. They never saw that metamorphism. You with me? Where do things change? Things change right here at the axis of the Alaskan orocline. So east of the axis of the Alaskan orocline, intense deformation, metamorphism. West of the Alaskan orocline, basin formation, preserved volcanic edifice. Okay, so you with me so far? Something's different. Okay. So there's a little brief history of the collisional work the work that we've been doing on this collisional belt along the length of the Canadian Cordillera. What I want to do now is return back to this paleomagnetic data that was used to talk about the Alaskan orocline in the 1980s. This here is a pretty famous figure from this Hillhouse and Co. paper in the Decade of North American Geology. And what it shows is all the paleomagnetic sites across Alaska, their latitudinal transport, which are these bold arrows shown, and then the vertical axis rotation, which are the things that look like little pieces of pie here. So if you don't know much about paleomagnetic data, that's okay. The point that you need to know for right now, like that spot right there, for example, the thing you need to know right now is that, say a lava flow erupts to the surface of the Earth and crystallizes, that lava flow will lock in the direction to north and south, actually, at the time that it crystallizes. And if you go and measure that magnetic vector nowadays, and if it doesn't point to north, you know that something has happened, okay? So what this is showing is that most of the places throughout Alaska don't point to north, okay? So what I did is I took all of these data and then I plotted them up on a graph of rotation magnitude, which is on the vertical axis here. So counterclockwise rotations are negative, positive rotations are clockwise rotations, versus age, so age on the horizontal axis. So these are all of those paleomagnetic data on a graph. And basically what I was trying to look for is there a pattern here? And I don't really see a pattern here. But one of the problems is that a lot of these data are from 1970s, 1980s, and we have a better idea now of what North America was doing during these times. And usually we need a reference pole, like North America reference frame, to determine whether or not these rotations are moving relative to North America, or is it just North America doing its thing. Okay? So all of these here are North America reference poles from the original sources from the 1970s and 1980s. So then what I did is I took those data and I replotted them with modern day North America reference poles, what we know now about what North America was doing during this time. I adjusted the ages because in many cases we know we have better ages on these rocks. So they've been redated, better techniques, lower or higher precision. And so I've adjusted things sideways a little bit if the age is better. And then I've color coded them based on what rock type they're from. So the dark red is the late Cretaceous igneous rocks, the pink are the Eocene igneous rocks, and then the green are the sedimentary basins, just like that map I showed you a few minutes ago. Okay? And still not a ton of pattern here, but then what I did is I took a trick from the geochronology community and I performed a weighted mean on these rocks. And if you're not familiar with a weighted mean, it's basically a way to average the data that emphasizes the analyses that have smaller uncertainties. So it makes the things with smaller uncertainty more important. Okay, so I performed that type of an average on these rocks, and what I want to point out, or on these data, and what I want to point out is this pattern here from about 70 to about 50. You can see that there's a stair step here where the averages over that time period show progressive decrease in the amount of counterclockwise rotation. Okay, so we're taking kind of a messy data set and we're trying to tease something out of it. And what we can see is that there's a little bit of a pattern here where we've got progressive rotation of Western Alaska from about 70 to about 50 million years ago. Okay? You can also look at these data, and I've just averaged a few of the sites here and put them back on the map, and you can see that almost every single data point in Western Alaska has been rotated counterclockwise relative to North America. Okay? So what this is telling us is that rocks that are late Cretaceous to Eocene in age, so about 70 to about 50 million, have been rotated counterclockwise in Western Alaska. Do you remember the significance of this time period, 70 to 50? Anything else on this map remind you of what's happening at that time? Crickets. Okay, that's all right. What else is happening at that time is that our metamorphism all along the margin from Washington State to Central Alaska, these rocks are undergoing metamorphism at pressures of something like 8 kilobars, temperatures of something like 700 degrees. Western Alaska didn't see any of that deformation and metamorphism, but what it did see is counterclockwise rotation at that exact time. Okay? So now what I want to do is take that information and wrap it up into a tectonic model. I'm going to be working on some restorations of everything inside of the white region here. We're going to play it backwards in time, and I'll play it forwards in time, backwards in time, forwards in time, and you can see where I'm going with this. And now I'll actually explain it. Okay? So here we are about 60 to 70 million years ago. Our metamorphic belt has been chopped up a little bit by the Denali Fault and other related structures, but if we undo the Denali Fault, we can see that we have a continuous belt of metamorphism that runs the length of the Cordillera from Washington State farther north to a restored position around Juneau. Okay? Our insular terrains are here in light blue. Our Chugach terrains are here in yellow. Another thing happening at this time period is that there is subduction of a mid-ocean ridge system offshore of the Chugach terrain, and it's going to emplace a series of plutons into the Chugach terrain as you go along the margin to the south. Okay, so the oldest one is the Sanak Island pluton that comes in at about 63 million years ago. Okay, so at this time, ridge subduction, collision, or at least shortening of the insular terrains with North America, creating metamorphism along this length of the Cordillera here. As you go out to western Alaska, no metamorphism, but you got sedimentary basins, and you've got widespread volcanism. Okay? Another thing happening in western Alaska is this thing right here, R, is this basin called the Rampart Extensional Complex. And what this basin is interpreted as is it's a normal fault bounded basin that exhumes kyanite grade metamorphic rocks and then dumps those kyanite grade rocks into a basin right next door. And it was active at this time between about 60 and 70 million years. It's located right there at the R, and I would interpret it as one of these little basins that has been proposed by Coe to exist right along the Orocline axis. So we've got bending of the purple terrains at this time, metamorphism between the purple and the blue all along the margin, basins forming, a bunch of strike-slip deformation out here in western Alaska, and then we've also got counterclockwise rotation of western Alaska at this time period from latest Cretaceous into earliest Paleocene. Move forward a little bit in time. The Tintina Fault has moved things to the north and then shut off. Our Rampart Extensional Complex is right there in the yellow star. The Denali Fault is going to form here around 50 million years ago, and it's going to take the insular terrains and the Chugach terrains and start shipping them north and then moving them through this curved part of the margin. Our near trench plutons that have been placed into the Chugach have migrated all along the margin and are now down here off the coast of Vancouver Island. This is also the time period that we see, or about the time period that we see the Silesia terrain and the Yakutat terrain have formed. They're splitting in half. Silesia is accreting to the margin here in Washington and Oregon, and then the Yakutat terrain is going to find its way up the coast to Alaska. All right, and we still got a little bit more rotation that's happening here in western Alaska. And actually, can we move that video? Yes. The other thing happening at this time period is that the Beringian margin is going to override an oceanic plate that's out in the Bering Sea, and this is going to initiate the Aleutian subduction zone. Okay? And then we'll go last to our 0 million years ago present day time frame, and this is what things look like. So we've rotated western Alaska now. Our metamorphic belt has been dissected a little bit. It's pretty well preserved along the Canadian Cordillera, but there's a little bit of it that gets chipped off here in southern Alaska and a little bit of it that gets chipped off here in the North Cascades. Yakutat has found its way up to Alaska, and Alaska is now a curved margin. We have preservation of the sedimentary and volcanic rocks in western Alaska. None of those rocks are preserved anywhere else along the length of the Canadian Cordillera. So we'll go back in time. And I have just a couple things I want to talk about here. So I had mentioned this Aleutians thing, that we get to the Aleutians. This is a recent paper by Bizard and others where they dredged rocks and compiled all the data of dredged rocks from the Aleutians. And they found that the oldest volcanic rocks in the Aleutians come in at about 48 million years ago. Okay? And the argument here is that that is when the Aleutian arc migrated, or initiated. So in my tectonic model, what that would look like is that rotation of western Alaska is going to cause convergence, and there's a chunk of oceanic plate that gets captured out here that is the Bering Sea plate. Some people think this is the Kula plate, other people think it's a part of the Farallon plate. Plates don't have name tags, so I'm not too worried about that. But what did happen is that there is a piece of Jurassic seafloor that got captured at this time, and the Aleutian arc is built on that seafloor. Okay? This has been talked about a lot by a person named David Scholl, and he's got this paper from 2007 where he argues for this process of moving stuff out to western Alaska, converging here in the Bering Sea region, and then the subduction zone is going to step out, capture a piece of seafloor, which he calls Aleutian, and that's going to initiate the Aleutian arc. His mechanism for doing all this is strike-slip faulting in the Cordillera, but what we now know about the strike-slip faults in the Cordillera is that they were not all active at the same time, and many of them actually weren't even active at 55 million. So I don't think strike-slip faulting and moving things from the Canadian Cordillera into Alaska, into the Bering Sea is a great mechanism to achieve this. But I think another logical explanation based on the metamorphism along the Canadian margin is that shortening between the insular terrains and the Canadian Cordillera is a good mechanism to do this. So in this case, we've got shortening here between the insular terrains and the Cordillera. So this is where our metamorphism is here along the margin. Western Alaska gets left out of that party. It wasn't invited, and instead it gets pushed out and extruded to the side toward the Bering Sea. That's what causes the convergence between the Beringian margin and that seafloor, and that's what initiates the Aleutian subduction zone. So this process of extruding crustal material out to the side of a mountain belt is not a new idea. This is certainly not my idea, and I'll call back now to this paper from the early 1980s, this is redigitized in the Fossen structural geology textbook. And basically what this paper by Tapignet did was they set up an analog model with some striped clay, and then they jammed a piece of metal into it and said, look, we made the Himalayas and Tibet. And the key part of this model that's relevant is that in this experiment, they generated strike-slip faults, which are these black lines that are curved, and those strike-slip faults extrude crustal material out to Southeast Asia. And it reproduces the first-order tectonic features of the Indo-Asian collision, where you've got strike-slip faults here, also in black lines that are curved, and crust is flowing from the Tibetan Plateau out toward Southeast Asia as India continues to collide with the Eurasian continent. So not a new idea. What I've done is I just took this basic model, I flipped it and spun it, so now we're looking at collision of the insular terrains with the Canadian Cordillera. Western Alaska, in this case, got left out and is being extruded out toward the Bering Sea. Okay, so I'm co-opting this, I think, pretty well accepted model for the Tibetan Plateau and using it to explain the Cordillera. Okay, so if we go back to the beginning here, what we're looking at here basically is changes in tectonic processes along strike of the Canadian Cordillera from Washington State all the way to Western Alaska. And if you remember back to the beginning part of the talk, I said that one way to make an orocline in the primary orocline mode is to change the plate boundary forces along strike of the mountain belt. And that's basically what I'm arguing for here, is that we've got collision here along the length of the Canadian Cordillera, and then Western Alaska didn't see that collision and is instead being extruded. That extrusion causes curvature, and that is the Alaskan orocline. So very briefly, right here, this is that paleomag graph again, and what I want to do is talk about these data right here, which have very large uncertainties. I'm fully aware of that, but they likely record a little bit of counterclockwise rotation. So I want to talk about a mechanism for that rotation as well. And that is related to the Yakutat collision. So since about 30 million years ago, the Yakutat terrain has been colliding with the southern margin of Alaska. It's down here in the corner. And what that has done is it has increased the shortening in the upper plate, and it basically moves crust through the curved Denali Fault out toward Western Alaska. So what we're doing is we're moving crustal blocks along a curved fault. When you move things along a curved fault, it's like driving your car on a curved road. You're going to have a vertical axis rotation of those crustal blocks. So we can get counterclockwise rotation just simply by moving things through a curved fault. And then we can also, with that shortening, have a little bit of tightening of that fold hinge that's related to this shortening in the collision of the Yakutat block. So again, this has been argued for the Indo-Asian collision zone, where basically what I've done here is just said, hey, look, they're mirror images of each other. We've got India colliding, extruding material toward all these subduction systems out here in the South Pacific. We've got Yakutat colliding, extruding crustal material out toward these subduction systems here in the North Pacific. So not exactly the same thing, but first order principles, it's a pretty similar process going on. Okay, so here we are, wrapping it up. Why is Alaska curved? And I would argue that Alaska is curved because the orocline formed progressively in response to terrain accretion in the Canadian Cordillera, the extruded Western Alaska. I think this explanation nicely explains the distribution of metamorphic rocks particularly late Cretaceous to Paleocene metamorphic rocks throughout the Cordillera. It explains the distribution of late Cretaceous to Paleocene sedimentary basins throughout the Cordillera. It works with strike slip or geology-based strike slip restorations, and it honors the paleomagnetic data that have been around for a few decades now that were basically the source of this tectonic model from the start. So what I'm trying to do is just make sense of all these data here and give you a tectonic model, something to chew on. So if you like this, it's been accepted to GSA today. I'm still waiting on page proofs, but hopefully you'll get to read about it at some point. So, any questions? I need water.
Thank you, Trevor, for an excellent talk. It's approaching 1 o'clock. If you've got a 1 o'clock class, can you just kind of quietly slip out? But I think many of us want to continue with Trevor with a Q&A. So do your quiet tiptoeing out of the room, please. And at the same time, Trevor, can we do some Q&A? And when you get a question, would you mind repeating the question so that everybody at home can hear the question as well?
Yes.
We'll just go for a few more minutes. Who's got questions here?
There's a question right here.
I have two things I want to ask you. The mountain range parallels the shoreline or the coastline. Is that not a coincidence? So could you have had something where like the ocean waves are kind of creating the mountain range through erosion, so distributing sediment this way to pile up to become the mountain range, and then pulling sediment away this way, which would wash away kind of the coast or the shoreline? And then could it also be something like the water, you have maybe like groundwater, or the ocean waves, or the ocean water forms sedimentary rocks, which creates earth material that's kind of ripe for upward expansion?
Yeah, okay. So if I understand the question correctly, is the mountain range is parallel to the coastline? You're particularly talking about southern Alaska, is that right?
Yeah.
Yeah.
Well, it could apply for other mountain ranges too.
All right, and is that related to the erodibility of the rocks? Is that a way to paraphrase?
Yeah, something along those lines.
Okay. So maybe,
Sure.
That the mountain range is like an old coastline or an old shoreline.
yes, the mountain range certainly is an old shoreline. Actually, this one might do it. The mountain range certainly is an old shoreline. Many of these are sedimentary rocks that were deposited in a nearshore environment. The interesting thing about the southern Alaska margin and the mountains that are there, so like these mountains here, the Chugach Range is what we call it, is that those mountains actually formed after the Orocline. So that is not an uplifted mountain range that has formed. That margin was curved, and what we understand about these margin, or this particular part of the mountain range here, is that those mountains were uplifted because the Yakutat terrain, as it was sliding under, removed sediment from the coastline and stuffed it under the continent, which uplifted those mountains. Okay? And so my take on why it's parallel to the coastline is that the mountains are controlling the coastline. They're uplifted, and wherever they're above sea level, that's your coastline. The other thing to consider in this part of the world particularly is that there has been intense glacial erosion here. So when you zoom out like this, it looks like the coastline is parallel to the mountain range, but if you zoom in, the coastline is actually like a spider web of fjords. So it's a little more complicated than that. But at a first order, yeah.
What you're saying with this, could that have been at some point in time like the ocean?
Could what have been the ocean?
What were you saying with like this slope here? That like push, I think.
Well, thanks for the question. We're going to continue to get different voices. We'll come back to you in a bit. Others for Trevor, please.
Oh, I saw two at the same time. Let's go Chris first, then Frank.
Trevor, enjoyed your talk.
Thank you.
One thing I was intrigued by, it looks like in this interpretation that insular terrain collision is quite a bit younger than what it is in some other models, and I just wondered if you could comment on that.
Yeah.
Could you repeat that, please?
Yeah, so the question, well, the statement is that in this tectonic reconstruction, the insular terrain collision is younger than other models that are out there, and you'd like a comment on it. Two things. One is that it depends how you date collision. So if we just look only at the sedimentary rocks and the basins, that basin was closed at 85 or 90. But the metamorphism that came in and fused these two terrains lasted until about 57. So it's a protracted process. I'm certainly aware at this latitude, people have argued that the insular terrains were here in probably the Jurassic or maybe even the early Cretaceous. Like I said, I've not worked in this part of the world, but if you look at the recent papers by Sauer and others, they basically argue that there's a foreland basin that existed between insular and whatever kind of North American stuff was in the North Cascades, and that entire basin was consumed at this time. So whether or not that's a collision or just intraplate shortening, it kind of depends on like how you define your terms there. As you go farther north, the basin certainly was open until 100, and as you go, and that was in southeast Alaska. In south central Alaska, the basin was open until 85. So one way to do it there is just by zippering. And in the north, we've got, I think, strong evidence that that basin closure shut off of sedimentation transitioned directly into metamorphism of those rocks. So in Alaska, I'll just say, at least mainland Alaska, there's not a lot of evidence for an early Cretaceous or Jurassic collision. But I know that that's been argued for in the south. And there's various ways to get around that, either zippering or collision reopening and reclosing. And I'll just say I'm not a British Columbia or North Cascades geologist, so I would just trust the people that have worked on that at this latitude. But in the north, we have no evidence for a Jurassic collision.
Other questions?
So, Frank.
Yeah, so you've invoked this kind of model analog with India as an underbelly glider, and you said, okay, well, we have first the, if I get this right, the insular terrain followed by the Yakutat terrain as that kind of underbelly glider that's kind of pushing up on Alaska. Did I get that right?
Yes, that's correct.
Okay, well, we still have India today in the Indian model.
Yep.
You know, it's still pushing up in the underbelly of Asia.
Yep.
What's pushing the Yakutat now to generate this continuing ongoing escape?
Yeah. Yeah, that's a great question. So as I understand it, the argument is that there's insular terrain collision followed by Yakutat terrain collision. What's driving those, and why is India taking so much longer? Is that maybe a good way to phrase it?
India's still going on.
Yep.
We still have this going on. I assume we still have this going on. So we have something behind the Yakutat.
Yes. Yes. So what is pushing Yakutat? Two things. And actually here we'll get into semantics of the forces that act on plates, which is that push is actually a relatively small force that acts on plates. The thing that actually matters is pull, is slab pull. So if you take a seafloor basalt and you metamorphose it to an eclogite, I'm going to go, this might be the best image even though they're smallest. You metamorphose it to an eclogite, that eclogite is more dense than the upper mantle. Okay? And that curtain of slab in the upper mantle is what drives the majority of plate motion. That's the largest force acting on plates. Okay? So India collision, the convergence here is in part driven by continued subduction down here. In the Cordillera, Yakutat has a slab that goes about out here like this, that's under there, that's pulling on the Yakutat.
Sorry.
That's right. And then the other thing that's happening, so there is a bit of a push here, and the push comes from the Pacific plate, which has a slab that goes all the way along the Aleutians, and it's pushing on the Yakutat right here.
So basically you're saying that the Aleutian subduction zone is driving or pulling.
The Aleutian subduction zone is connected to the Pacific plate, which is pushing on Yakutat, but Yakutat has its own subducted slab, which is pulling on Yakutat. Yeah. Yep. And it's relatively small, but it covers a region something like this underneath southern Alaska.
Is there a tomography for that?
There have been some tomographic studies. More recently, a lot of it are not strictly tomography, but there's things like receiver functions where people have imaged the slab with receiver functions.
A few more?
So I see a question here.
On one of your maps, you showed magmatic belts between the insular terrain and the previously accreted terrain.
Yeah.
And you showed two different ages of magnetism in there. Older magnetism outboard and younger magnetism inboard. What do you attribute that to?
That's a great question. So the question is that here along this figure, I've got two phases of magmatic rocks. The dark red is older and it is outboard, meaning nearer to the coast. And the younger stuff is in the light pink. It's inboard, meaning nearer to the continental interior. What is the explanation for that? Generally, distribution of magmatic rocks along plate margins is not always systematic because it's largely tied to slab dip. If you change the dip of the slab, you can widen the arc or push the arc in one direction or another. So it could be related to that. I don't think that's exactly what's going on here. My take on this distribution of magmatic rocks is that the older stuff is quite flattened and it largely follows that suture. So there's plutons being placed into the lower crustal suture and they're also being intensely flattened as they're being placed. So this will work. The areal extent of that magmatic belt is much smaller than it would have been if it wasn't deformed. So we took a big pluton and we just smacked it down to something very, very thin. So that's part of it. Then the other part of it is that the pink here are plutonic rocks that are largely associated with oblique extension. So this time period here around 45 to 60 is the birth of the Denali Fault and the birth of the Queen Charlotte Fault. So we've got distributed strike slip deformation at this time and then extensional fault systems associated with the ends of those strike slip faults. And a lot of this magmatism here is related to that process. So the widespread distribution, like here in southern British Columbia, for example, a lot of that magmatism is genetically related to the extension. And it's focused in these zones of the crust that are pulling apart. So it's not as simple as slab dip, although we'd like to think it is. Yeah. So another question?
Yeah, how does this affect the Brooks Range? Is it bending it, shoving it in there? Because we got the Yukon Valley, Brooks Range, then the Arctic Slope.
Yeah. So the question is, how is this related to the Brooks Range? And as you can see from, let's see, this image here, I'm conveniently ignoring the Brooks Range. But the justification for that actually is that the Brooks Range and a lot of what is in west central Alaska was actually not there at this time. It's likely been moved in along strike slip faults, and there's been some shortening and actually some extension too, depending on where you go, that has happened since or over this time frame. So I would argue that these things I'm talking about here are actually decoupled from Brooks Range geology. There's a big, this fault right here is some sort of, and it actually continues up into there. It's a very cryptic, huge structure that separates what I would call the Cordilleran realm from the Arctic realm. And they're completely different geologic histories. And especially if you do, these stars here are minimum strike slip restorations. So that's the minimum amount you have to take this stuff and send it south since 70 million years ago. So if you just do that, you're gonna send this stuff south 1,500, 2,000 kilometers. So yeah, they're maybe the same city, but not the same neighborhood.
Hundreds of miles apart.
Yeah.
Hey, let's thank Trevor one more time for an excellent talk.
All right.
Thanks for coming. We'll see you in 2 weeks. If you've still got questions, come on up, and I'm sure we'll have a little smaller group off microphone. Thank you for coming.
Thanks, everybody.
You may have said something against this idea, but could there be something coming up from the tectonic plates? It's kind of like a volcano.
I'll be with you guys in just a second. I want to say goodbye to you all and make some comments about this talk. I just have to unplug this big speaker here first. Okay, I assume we're still communicating here. Can I say a few things before we sign off? Number one, thank you for watching this. Many of you were watching live. I think we had more than 400 watching live, which is a bigger number than normal. So that interest is there. That's wonderful. Number two, this is a timely talk. In addition to our speaker, Trevor, being close friends with Hannah Shamloo and Jordan Carey, in addition to that, connecting with Trevor and making a few interviews with him on my YouTube channel helped prompt me to do this new alphabet series, A to Z. So I think Trevor will be a key person this winter, and that talk was, I thought it was dynamite. I don't know how you feel about it, but it had just the right approach that I'm hoping to do. So we've already had breakfast and talked most of the morning about ideas for what we may do, but I'm going to continue to lean on a young guy like Trevor Waldien. So I saw that Robert Hildebrand was with us live, and that was a nice surprise. So Bob, if you're still with us, that's a special treat. Thank you. And we'll have many of the deep thinkers as well as more conventional thinkers involved this winter. So there's a subset of folks sticking around, chatting, and made the trip to visit with Trevor. And Trevor will be here most of the weekend, but not tied to geology. He's going to be out hiking with his family and everything else. So I will see many of you live in 2 weeks if you want to come back. October 24th, Mitch Allen from Washington Geological Survey talking about landslide mapping. And then Halloween, our last Friday noon talk of the quarter, will be Emily Richard, also from the Washington Geological Survey. So hoping to visit with you then. And then November, is it the 6th? Thursday, November 6th at 3 o'clock Pacific time, we will be starting Alaska A to Z, 2 live streams per week, and I'm very much looking forward to do that. I have all the stuff that I have together in my head, at least to get us started. And then like every other A to Z series, we'll just see where it goes. We'll just see where it goes. All right, thanks everybody. I love you and goodbye from Ellensburg, Washington, USA. Hope you enjoy the weekend.